자기 자신 그리고 타인과 소통하라. 한국 청년들에게 보내는 소통의 메시지가 참 인상적인데요. 그렇다면 데니스 노블 교수가 자신의 분야인 시스템 생물학에서 말하는 소통이란 무엇일까요? 이번엔 청년들이 함께했습니다.
I thought I would begin by explaining a very important question, which is this. Just over 10 years ago, I published a book called The Music of Life, and it challenges some of the major ways in which biology as a science was presented to the public during the 20th century, as all depending on the molecules that form our bodies, and in particular, of course, the genes that form our bodies, and which were therefore thought to be, to quote a famous book, Richard Dawkins' Selfish Gene, they, genes, created us body and mind. And I claimed in this little book that that just isn't true. It's the other way round. We constrain the molecules of our body to do what they do. So you might well ask, having written that, why should I go on 10 years later and write another one? Well, first one, of course, to say about that is that this is actually a different book, even though it's got a title that also has hints of music and so on in it. But you know, there's an interesting saying in English, comes from a nonsense poem, The Hunting of the Snark, and the saying is, what I say 3 times is true. Well, I've said it once, I'm now going to say it twice, and perhaps when I say it 3 times, people will believe me.
옥스퍼드 퀸스가 20세기를 풍미하는 어떻게 보면 되게 세력이 있는 거잖아요. 그 이론에. 근데 그거에 반기를 들 때 약간 두려움이나 이런 것들이 있진 않았는지 궁금합니다.
But to answer the question, no, I have no problem at all. I'd like an attack. I want a debate. So, yes, I thought, though, that this time I would start by trying to shock people into debate by posing some very fundamental questions, like what happens when you look up at the sky at night? Now, hopefully, in a deep part of the countryside, not here in Seoul where there are too many lights, but, you know, up there towards North Korea or way, way down into the south of your country. And when there's a moonless night, look up at the sky, and what you see is utterly incredible. And of course, our ancestors must have seen this all the time before their houses were lit up. They would see countless stars appearing and a great band, like a belt, going across the sky, which of course is seen from a particular position. That's our galaxy, that's our set of millions, even billions of stars, of which our sun is just one. So I thought I'd pose to people the question, what do you think when you see all of that? Don't you find it impossible not to ask the question, why? Why all of that? And why are we here to witness it? So that's the question with which the book begins. If I may just use Richard Dawkins yet again, you see, but he's not alone in this. He would say, look, Dennis, there's no problem. Science can answer all of those kinds of questions. We're here because, well, it just happens we're here. It's all chance, all blind chance, the way our bits of DNA happen to have mutated in particular ways. And then, of course, the process which we all know about as we learn biology at school of natural selection. The successful organisms survive, the less successful ones don't. So it's obvious. But my reply to that is, wait a minute, there's a problem with that, because that doesn't actually answer the question, why all of that? And it certainly doesn't answer the question that the great astronomer Martin Rees pointed out when he calculated that if the constants that determine the way in which matter in the universe interacts were even just slightly different from the ones that they are, one, the universe as we know it would not exist. We would not exist. And his point is very simple. Unless you can explain why those constants are as they are, you haven't given an explanation of why all of that up in the sky exists. Nor have you given an answer to the question why you exist. So the question is still there. Now, of course, previously our ancestors might have said, well, it's fairly obvious, you know, all of this, our Earth is the center of the universe. Well, I'll show you our Earth from about 1 billion miles away, and looks like this. Viewed from that spacecraft that went around Saturn with its beautiful rings, we appear just as a tiny dot. Doesn't look much like the center of the universe, doesn't it? So I put a few questions, you see, which is, like I say here, if you take astronomers seriously, they're very worried. They know that actually when it comes down to fully answering the question, why does all of this exist, we don't have a proper answer. Okay, so far you've got a question.
그 별이라는 게 하나로만 봤을 때는 그냥 별인데 별이 여러 가지 별이 이제 이렇게 모였을 때는 아름다움을 줄 수 있고 하나의 의미가 될 수 있잖아요. 근데 이제 노블 교수님이 전공하신 시스템 생명학이라는 게 이제 하향식과 상향식이 어우러질 수 있는 그런 통합적인 관점의 학문으로 제가 알고 있는데요. 혹시 그런 관점이 이제 어떻게 보면 우생학 내지는 좀 그런 하나의 개념적인 것과는 좀 배치되는 부분이 있는데 교수님께서 생각하시는 가장 그런 중요한 철학적인 근거가 뭐가 있는지.
좋아요. That's a very good question, which is going to come a little bit later, but why don't I go straight for it now? You see, I think there is no reason whatsoever why, in thinking about causation in our bodies or in the universe, there's no reason why we should privilege any particular object in the universe as a cause. And that means, for example, that there's no guarantee that molecules are everything, as some biologists will tend to say. Moreover, I actually think that all levels of organization, from down at the bottom at the quarks, through to the atoms and molecules, through to the genes of our bodies, through to the cells, the tissues, the organs, the system as a whole, and then the environment, including the universe as a whole, all of that can have causation going both ways. And the reason for that is very simple. It is that all organisms are open systems. They necessarily interact with the environment, so the environment is as much a cause of what happens as any molecules inside our body. I call that the principle of biological relativity, meaning there's no privileged level of causation.
시스템 생물학이 오픈이라는 걸 강조하는 거라고 제가 이해를 했는데 그러면 범위가 너무 넓어지는 거잖아요.
넓어져서 이해하기가 더 어렵지 않게
네,
되는
그리고
거죠.
이제 이게 맞다는 거를 입증을 하는데 되게 어렵지 않을까 이런 생각이.
Yes, not true, and I'll explain why. Right? Now, how would you calculate the behavior of the individual molecules? I'll tell you how you do it because I do it. You set up what are called differential equations. They just represent the laws with which each of the components moves in a particular way, like billiard balls knocking into each other this way and that. Those are the main equations that you would use in trying to represent either the development of the whole universe, or a process in our body, how a heart beats, or how a gene can interact with the various things that tell it what to do to make proteins. All of that, you'd have to use differential equations. Now, there's an absolutely fundamental fact about differential equations, which any mathematician can tell you. Without what are called the initial and the boundary, that's the environment conditions, there's no solution. Absolutely none. So right down at the bottom level, when you start to calculate the movement of the individual molecules, you're forced to ask the question, like Martin Rees asked of the universe, what are the conditions, the constants or the initial and boundary conditions that constrain the equations, or rather the motions of the molecules, to do what they do? So you're faced with the difficulty right at the bottom level of trying to reproduce anything that is a mechanical interaction. You need the context as well as the process. And we can prove that with a very interesting everyday experience. When you go up in a balloon, there are trillions upon trillions of gas molecules in that balloon. Now, if those gas molecules were not constrained by the existence of the balloon, they'd go every which way. You certainly wouldn't be carrying people. What's happening there is a simple lesson from physics. Even though those molecules are bouncing around in a random way, notice I said random, that brings in the chance aspect of things, and chance is an important part of life too. But even though those molecules are bouncing away this way and all which way, in a random way, at the level of the balloon as a whole, everything behaves as a nice, simple set of equations relating the pressure, the volume, and the temperature of the balloon, and whether it rises or falls. That tells you that physics is a very interesting, multi-level kind of science, because it says that at the level of the molecules there will be chance. At the level, though, of a larger organization enclosing those molecules, things will be more beautifully determined. Now, what encloses the molecules in our body is the cells of our body. They are like balloons. They actually are oily things that have been blown up to a particular size. Of course, they're very tiny balloons, but they are in effect. They're more like soap bubbles than balloons. But still, those are what give the constraint on the molecules of our body. Moreover, if I may just go on just to one other thing first, that constraint is exerted by a communication system of enormous complexity. That is part of a cell. But it's viewed in a very interesting way, because what's been highlighted with those greenish, yellowish, fluorescent indicators that are showing up the roadway or communication system of the cell are the filaments that run from one edge of the cell to another, and most importantly, they run all the way down to the nucleus to enable the nucleus, the DNA, to know about an event that occurred at the surface and change what is happening down at the level of the DNA. DNA, therefore, is itself under control. That's the lesson from physics, from balloons and cells, and where DNA is.
우생학은 나치로 하여금 제2차 세계대전도 발발시킬 정도로 어떻게 보면 그리고 사회에서는 사회 진화론을 만든 또 하나의 이론적 근거가 됐다고 생각하는데요. 노벨 교수님이 말씀하신 이런 부분은 어떻게 보면 이제 그 사회 진화론 같은 그런 우생학을 극복할 수 있는 하나의 대안이라고 저는
전혀 다른
네, 대안이 될 수 있다고 생각을 하는데 그거에 관련돼서 이제 교수님의 견해가
That's a very nice question. Very nice indeed. You see, ask the question, where did the justification for the killing of 6 million people, Jews, Poles, Gypsies and others, during the Second World War, where did that justification come from? It came from the idea that some people were deficient in their genomes, literally so, inferior human beings, and therefore it was perfectly reasonable to say they could be killed. The same thing happened in this part of the world. The so-called rape of Nanjing, which was when the Chinese were slaughtered in large numbers in Nanjing. People treated them as though they were animals. Now, where did that idea come from? It came from a 19th century interpretation of the Darwinist idea of evolution. And the idea was very simple. It was this, that the poor, who were thought to be the inferior human beings, were reproducing rapidly. It's true. The rich were thought to be the superior human beings, reproducing slowly. Prediction, humanity would decline terribly quickly into a pretty low state. What that ignored was that the genomes of nearly all human beings have got advantages and disadvantages. And there is no guarantee that people who are poor, who happen to be of a particular ethnic origin, like Jewish or Polish, will be inferior to people who are from another ethnic origin. In fact, if there was any evidence at all, what was Einstein? He was Jewish. Or Schrödinger, he was Jewish. If there was any evidence at all, it would actually be against the Nazi interpretation of the nature of humanity. But if you ask the question, where did that justification come from? It's very clear that it came from the sociological applications of what were thought to be the best interpretation of Darwinism. Now, I don't blame Darwin. I think he was misinterpreted in that. But there's no doubt, I think, that there was a clear correlation between the science of humanity, the science of our genetics, and the idea that some people could be regarded as very inferior, and therefore it didn't matter if they were gassed, slaughtered, burnt, or slaughtered. I would like, though, before we go on to some more interesting questions, I'd like to just present to you a little calculation. And again, it comes from looking at the universe. This is no longer looking at the sky at night, because this is actually looking at a region of the sky which, if we were looking at it now, it would look almost completely black. It's one of the darkest corners of the sky that you can observe with a telescope. And this picture was taken by the Hubble telescope up there in space, looking at that dark region for 10 days, collecting all the light that came from stars and galaxies that are unimaginably distant away from us. For some of them, it's taken 13 billion years for the light to travel to us, to enable them to show up as a speck of light on this so-called deep field view. Now, my calculation is very simply this. That's just 1/80th of a million of the sky. It's a terribly tiny part of the sky. But you can calculate, you can count the number of galaxies there. You can then expand that up to the whole sky. And you can ask the following very interesting question: how many atoms are there in the universe as a whole? So, we can do that calculation. The answer is 10 to the 80. Now, I also did another interesting calculation that's just above it. I worked out, suppose there are about 25,000 genes in our body. How many interactions could there be between 25,000 genes? It's 10 to the 70,000. It's absolutely hugely greater than the complete size of the universe. Now, a very important set of conclusions comes from that calculation. The first one is the one that's on the screen, that it would have taken more than the many billions of years that life has existed, roughly 4 billion years on the Earth, to explore even a tiny fraction of those possible combinations, from which I draw the conclusion that life has to have had some kind of directionality. If you think about it, there's a space there, mathematically, which is absolutely enormous. We are the product of a very tiny corner of that space, mathematically speaking. And it just doesn't make sense to think that all of that little needle in a vast haystack has been found by chance. I'll bring chance into it and then go on when we've thought about that calculation. I think that nicely leads us to the central point of the talk. So I'll come to that. What is the point? And I've got it up in these questions, you see. The standard story, the one that you'll find in The Selfish Gene, is that there's blind chance and then there's natural selection, so there is absolutely no purpose. That's a tough story, but if it was true, you'd have to accept it, wouldn't you? I mean, that's the best way to look at science. If it tells you something that's a bit uncomfortable, don't complain about the science, complain about you feeling uncomfortable. But I don't think that's true. And the question, the very deep question that I ask in this book is, could evolution have evolved purpose? Now we can show that it must have done. I want to just take one example of how we can show it. When you are invaded by a virus or by something else that attacks you, what happens? It's your immune system that reacts to defend you. How can it do that? Because there are absolutely trillions of possible ways in which a virus could be formed to invade you. And in fact, viruses are evolving all the time. Even with 3 billion base pairs in the genome, there isn't enough combinations to have the possibility of forming an antibody to every one of the possible invaders. So what's the solution? I'll tell you what the solution is. When the invader comes, those roadways in the cells that I showed a bit early on get activated to tell the genome there's an invader. And what it then does, it tells the genome in a very particular small part of the DNA that is coding for the proteins that defend you, and say, please mutate, and do so very rapidly to produce as many possible variants as you can, because we haven't got one yet, we haven't got the key to that lock. What then happens is, as soon as one of those variants appears that works, the system then says, reproduce, you're good, you can invade, you can now invade the invader and stop it. What that tells you is that it's perfectly possible for the body to tell the genome to do something perfectly purposeful, targeted at what is needed to produce the response to the environmental challenge. So what that means is that organisms do have, you could call it the intelligence in inverted commas, because we don't think about that, we let our immune systems do it. But organisms, even very small, tiny organisms, have the capability of doing purposive things. The same process occurs as life evolves. Now let's take one of the most primitive forms of life, bacteria. They get invaded by viruses too. They have the same problem that we have. They use exactly the same mechanism. That is, they receive a signal from the environment saying it's bad, there's an invader. And that also tells their genome to start mutating very rapidly. Now what that means, of course, is that different bacterial cells will be produced, some of which will be appropriate for coping with that situation, some of which will not be. There will, of course, be a natural selection. Natural selection still exists, so does chance. So the two central features of the standard story, chance followed by natural selection, are still there in the story that I tell. But over and above that, there's exactly the same kind of purposiveness in the process that I described in the immune system. All organisms can do that. All organisms, therefore, as a population, not now as a single organism, all organisms can partially see the way forward to evolve that particular type of organism to cope with an environmental challenge. That is the inheritance of an acquired characteristic. And I've chosen those three words, inheritance of acquired characteristic, because that's the very process the standard story says should not happen. It was actually a story produced by Lamarck 50 years before Charles Darwin, and incidentally an idea that Charles Darwin himself also accepted. So evolution also evolves. Charles Darwin worried about this question, worried about it a lot. He was a very cautious man. If you read his book, it's a marvellous book, The Origin of Species. He's very cautious about the way in which he developed his ideas. He had one very big problem with the idea that everything was chance variation and then just natural selection. And he asked the following question: what do we do when, as human beings, or as dogs, or as monkeys, or as rats, or whatever, we exercise choice in sexual selection, meaning who we choose to mate with? You ask the question, why women look beautiful is because men who need to look handsome, and it's women, of course, who choose them to be handsome, have chosen them to be so. There is a choice there. There is a directionality in what we've done. We, therefore, have actually created the beauty that we see in ourselves. That's a very funny way of putting it, but it's not a bad way of putting the dilemma that Charles Darwin saw. He saw that it couldn't be that everything was simply blind chance followed by natural selection.
They understand.
Understood? Well, I'll tell you more about sex then. But perhaps we should try and draw this to some kind of conclusion, shouldn't we? I don't know how long this is supposed to go on, but let me see just what else I've got here that I should talk briefly about. Now, I think we're almost there. Let me see if I can sum up what I'm trying to say. What I'm trying to say, I think, is summed up in the following kinds of ways. First of all, there's no philosophical reason why we should privilege causation from any particular level in the universe or in organisms. In fact, if I just go back to that slide, this one, you see, shows the huge range of scales, all the way from quarks down there through atoms about 3 orders of magnitude up, organisms over there, human and the whale, right up to the size of the solar system, and then the size of a galaxy and the size of the universe. There is absolutely no philosophical reason why we should prefer to say that causes that, not that causes this. That's the first principle that I come up with. That doesn't mean to say that we shouldn't investigate what caused what, but we shouldn't assume in advance that we know what causes what, right? Moreover, we should pay attention to some very important experiments, and the following is a very important one. If I take DNA out of its cell life context and I put it in a dish with as many nutrients as you might care to put there, and a few lipids if you like to, whatever you want to mix up there, I could keep that DNA for 10,000 years. It would do absolutely nothing. It created us body and mind. You see, it needs the cell to tell it what to do. But it gets worse. When it tries to reproduce itself, it can't. The idea that DNA is a replicator is incorrect. It's the cell that makes it replicate. Moreover, why is it wound in a double helix? A really famous discovery that Watson and Crick made, on the basis of which so much of modern biology is being built. It's because if you unwind it, and there's a mistake here compared to there, you can tell that there is a mistake. So the system that is looking at the DNA to make sure that it's replicated accurately can correct it. So, one more calculation for you. And I promise it's the end of mathematics, in this talk anyway. How many errors does DNA make naturally when it copies itself, or when the cell allows it to copy itself? It's 1 in 10,000 base pairs. That's 1 every 10,000 nucleotides. In a genome of 3 billion base pairs, that's millions of errors. We know, in fact, that each time our cells divide, only about 1 error or 0 occurs. What happens? The system comes in with that famous double helix. It uses the comparison to work out how to correct 99.999% of the errors. The famous replicator, the immortal replicator, is actually made to do so by the cell, by the living cell. It's not the DNA that can do that. DNA is important. We wouldn't have genes if we didn't have DNA. But it doesn't create us body and mind.
저 질문이 하나 있는데, 이제 교수님께서 발표하신 그런 이론이 기존에 있던 학계 이론을 이제 좀 보완하고 그런 역할을 한다고 생각을 하는데, 시간이 지나면 이제 또 교수님의 이론에 대해서 어떤 반론이나 이런 게 나올 수 있다라고 생각을 하는데요. 혹시 그렇다면 지금 교수님께서 하신 이 연구에서 좀 더 보완하고 싶은 점이나 좀 생각하시는 한계가 있다면 어떤 게 있을지 좀 궁금합니다.
The day when my idea becomes orthodoxy, I think I will start thinking very carefully to see if I can undo it. Yeah, you've got a really good point, which is that, of course, science continually challenges orthodoxy. Once something is called orthodox, there should be some people challenging.
Yes.
Now, they may fail. That's fine too. All science advances by producing hypotheses, ideas, only a few of which will turn out to be useful, and even fewer will turn out to be correct. And at the end of the day, we'll still be facing that question that Martin Rees posed. Why are the constants of the universe so finely adjusted that our universe exists and that we exist? I've no idea what the answer to that question is. Even worse, he doesn't, and he's the astronomer royal. And even worse, I don't think anybody else at the moment can at least produce a reasonable way in which we can answer that very fundamental question. My view is, until somebody can answer that, we don't know why we're here, and we certainly don't know whether the universe has anything that can be described as purpose. You'll find many more in this book.
I will go to the bookstore.
Yes. Are you going to buy it?
To buy that book.
감사합니다.
이 세상 모든 것은 분열되고 단절된 것이 아니라 하나로 연결돼 소통한다는 것. 데니스 노블 교수님의 말씀 잘 들었습니다. 이 메시지가 우리 한국 청년들에게 전하는 뜻은 무엇일까요? 이것으로 청년정책소통포럼 연사와의 만남 마무리하겠습니다.